All right, today we're going to talk about Gauss's law. And I'm going to hit you straight up with Gauss's law here. I'm going to give it to you first in kind of words before we symbolize it. So Gauss's law is kind of a fundamental physics law about electricity. It says that the net electric flux through a closed surface is equal to the charge enclosed by that surface divided by epsilon naught, which is a constant. Now, we've already talked a lot in your studio and the Get Ready videos from Monday about finding electric flux and dealing with closed surfaces. Got a closed surface right here that we're going to use in a minute. We haven't yet talked about finding the charge enclosed by a surface. Some of the time, it's really easy. You just have to draw your surface. Here it's the little kind of red-orange line. And then count up the charges that are in there. Not really too hard conceptually to kind of add up Q1, Q2, Q3, Q4. Some might be positive, some might be negative. You have to take into account the positive and negativeness of the charges. But some charges might be outside of your closed surface. And surprise, surprise, you don't count them. So you count all those guys up. And again, you divide them by epsilon naught, and you end up with a kind of symbolized version of Gauss's law. That looks like this. Again, that kind of double integral over a closed surface that we saw earlier this week. And then the charge enclosed is just add up all those charges, Q enclosed, and divide by epsilon 0. Excuse me. And if you're not familiar with epsilon naught, you can see down in the corner, it's just related to the constant K that we've been using from Coulomb's law. So this is what Gauss's law says. Now, the burning question that you probably have here is, but why? Why do I need this law when I already know a whole bunch of stuff about electric fields? Gauss's law is useful for us for basically one purpose. It will let us find the electric field in very specific cases of high symmetry way more easily than doing a Coulomb's law integral like we have been doing over the last week or so. Now, the point there that's really critical is that your system has to have the right symmetry. Because that integral that you can see, the double integral with the circle around it, actually, that looks kind of scary. I don't know if I want to do that integral. I might want to do the other integral. It didn't look that hard. But in some specific situations, this integral actually is way, way easier. And those situations are if the electric field and the dA vector for your surface are parallel to each other, and if the electric field is uniform everywhere along that surface. I'm going to go ahead and show you the kind of most straightforward example here, and then we'll do a little bit of a trickier one in class. And we already talked a little bit about how to find the flux for this situation in an earlier video. I'm just going to think about a point charge. So I'm going to go ahead and draw us a little point charge. There it is. It's a little red dot. I know how big it is. Maybe it's got a total charge of, let's say, plus Q. And I want to see if I can use Gauss's law to find the electric field that this charge creates. Now, of course, I know the answer to this. I know what the electric field of a point charge is. So my goal here isn't really to figure out what it is. It's to see if this method will give me the right answer. So what I want to do is, to start out, use Gauss's law. I need a Gaussian surface. I need an imaginary surface of some kind. And there's a lot that you might think about, right? You might think about, well, I could draw like a kind of a square or a cube around here. I could draw like a cylinder around this thing, right? Here's kind of a cylinder shape. I could draw a sphere around there, something like that. Lots of things that I could draw. And I want to figure out which one of those many things I want by taking a look at my conditions. I need a surface for which the electric field and the area vector are parallel, and where the electric field is uniform along that surface. Now, the only way I'm going to be able to kind of make a good guess here is if I already know something about the electric field. So there's a little bit of cheating that happens in Gauss's law, which is that I know just from the symmetry of the charges. I've got one charge sitting there in the middle of the universe. I know for sure, even if I don't know how big the electric field is, that it's going to point radially outward or inward if it's a negative. And I'm going to go ahead and draw that on my little picture here, right? So I know that this electric field is going to point radially outward. There, something like that. I'm a terrible drawer. And so if I want to pick a surface whose area vector is always parallel to that outward pointing electric field, then I need to pick a surface that also has an area vector that points radially outward. And we already saw in the earlier video what that is. That would be a sphere. So if I draw a sphere centered on the point charge, then I get that E and dA are always parallel. I'm going to, again, not assume I know how big that electric field is. I'm just going to assume that the electric field here is purely radial. So E equals E, this is an unknown E times R hat. This should have been a vector over here. And then I know what the area vector for the sphere is, right? I can say A here is equal to dA times R hat. Now, one other really important thing is this part right here, which again, we talked about in the earlier video, is that that electric field's magnitude needs to be constant everywhere on the surface, uniform, no change in the electric field as we go around. And again, we can see that that is true as long as I stay the same distance from the little charge. So I need to pick this sphere not just to be a sphere, but to be centered on that point charge. When I do that, just like we did the other day, I can easily resolve this integral, right? The E is constant, the dA integrates to give me just the surface area of the sphere. The R hat and R hat vanish in the dot product and just give me 1. And so the left-hand side of this Gauss's law equation simply gives me E, which is this unknown electric field, times 4 pi r squared, where r is the radius here of the Gaussian surface, right? So if I picked a bigger Gaussian surface, I'd have a bigger value of r in there. Now I have to find the other side of this Gauss's law equation. And the other side is I want to find the total charge enclosed. Well, so I go to my picture and I say, there's only one charge, plus q. It is enclosed, it's inside the sphere. So I'll put plus q here, and I'll divide it by epsilon 0. And then I can solve this thing for E. And lo and behold, I get q over 4 pi epsilon naught times r squared. And we know from the previous slide that 1 over 4 pi epsilon naught is the same little k that we have been using for Coulomb's law. Notice that this method for Gauss's law didn't find the direction of the electric field. We already knew something about the direction of the electric field. If I want to get the full answer here, I've got to put that back in. So I got to go E is then going to be this times R hat. The other thing that you'll note is that this method worked because I only had one charge. It had a really high symmetry. And so if I start like throwing extra charges into my world, maybe I put another positive charge over here. This is another little plus q. I can still say Gauss's law is true, right? I still know that the integral of the E dot dA around the original Gaussian sphere that I've chosen, that's still true. In fact, it's still the same value because q enclosed over epsilon naught hasn't changed. But the electric field is no longer this friendly uniform picture, right? The electric field now, if I kind of erase all of these guys, I didn't mean to erase the plus q, but we'll live with it. The electric field now, kind of on this side, well, it's going to be kind of smaller than it used to be. Over here, it's going to be bigger than it used to be. And then it's going to not quite point perpendicular anymore because I've got superposition adding up due to the other charge over there. So I'm going to get some weird picture like this. The integral now is hopeless, right? That integral is going to be a different electric field, a different direction, a different magnitude everywhere around the sphere. It's not that Gauss's law isn't true, it's just no longer helpful. So you're only going to ever use Gauss's law when you've got really, really special symmetric cases like this one and the one that we'll do in class.